Good morning all. The next topic is magnetic torque. In this section, we will see what happens when you suspend a rectangular coil which carries a current in a uniform magnetic field. Here we see the special case when the plane of the coil is parallel to the magnetic field. Consider a rectangular coil PQRS of n turns suspended in a uniform magnetic field. It is suspended in such a way that it can rotate about the vertical axis y dash, that is shown in figure. The rectangular coil is named as PQRS and you assume that it has n turns and it carries a current I. A current I that is flowing through the coil PQRS which has n turns and that is suspended in a uniform magnetic field B. Now consider the case when the plane of the coil is parallel to the magnetic field. Now let us calculate what is the force on the arm PS, SR, RQ and QP. Now what is the force on the arm RQ? The force experienced by the section, the current carrying segment RQ when it is placed in a magnetic field is B is given by F1, that is integral I cross B dl1, where dl1 is a small elemental length in the segment RQ, that is I into dl1 cross B. Now if you see the figure, you can see that dl1 and B are in the same direction. So the angle between dl1 and B is 0. Therefore, the integral becomes I dl1b sine 0, which is equal to 0. That is, the force on the arm RQ F1 is 0. Similarly, find the force on the arm PS. The force on the arm PS. Let it be F3. The force on the arm PS F3 is integral I cross B dl3, where dl3 is the small element of length on the segment PS, that is equal to I into integral dl3 cross B. Again, the angle between dl3 and the magnetic field is 0. So the force on the arm PS, that is F3, that is also 0. Now let us consider the force acting along the arm QP. Let dl2 be the small element of length in the segment QP. Then the force acting on the arm QP is nothing but F2, that is equal to I into integral dl2 cross B. And if you observe the figure, you can see that the angle between dl2 and B is 90 degree. So F2 becomes IB dl2. Let L be the length of the coil. Then from the figure, you can conclude that integral dl2 is nothing but QP, and QP is the length of the coil. Integral dl2 equal to L. Therefore, the force acting on the arm QP, that is F2, that is equal to IBL. This is the magnitude of the force acting on the arm QP. IBL. Similarly, the force acting along the arm SR can be evaluated. The force acting along SR, let it be F4, that is I into integral dl4 cross B. This is equal to I integral dl4b sine 90, because the angle between dl4 and b is 90 degree. So the force F4 becomes, the magnitude of the force F4 becomes F4, that is equal to IB integral dl4. Again, observe the figure. If you integrate dl4, you will get the length SR. SR is nothing but the length of the coil, that is integral dl4 is L. Therefore, the magnitude of the force acting on the arm SR is nothing but IBL. Thus, it is clear that the force acting on the arms RQ and PS is 0, whereas the force acting on the arm QP and SR is IBL each. The force acting on the arms RQ and PS is 0, whereas the force acting on the arm QP and SR is IBL. Now we can see that the force acting on QP and SR are equal and opposite, whose magnitude is IBL. Since they are equal and opposite, they form a couple, and as a result, the coil is rotated in a magnetic field. The force acting on QP and SR are equal and opposite. They form a couple, and they tends to rotate the coil. That is, if you suspend a coil, a rectangular coil in a magnetic field, the coil will experience a torque. Now let us evaluate the value of the torque. To find the torque acting on the coil when it is placed in a magnetic field, let us draw the diagram once more. Let B be the breadth of the coil. Let B be the breadth of the coil. One force is F2 and other force is F4. And the distance between the breadth of the coil is B, and one force is F2 and another force is F4. How to evaluate torque? Torque is basically the product of one of the forces into perpendicular distance. The torque acting on the coil is obtained by multiplying one of the forces with the perpendicular distance. Here the magnitude of the force F2 or F4, whatever it be, it is IBL, and the perpendicular distance means the breadth of the coil, that is IBL into B. The perpendicular distance is actually QR and PS, that is equal to B, the breadth of the coil. If L is the length of the coil and B is the breadth of the coil, then L into B becomes the area of the coil. Therefore, we can write tau, which is equal to ILBB, and we can represent it as tau is equal to IAB. Tau is equal to IAB, where A is the area of the coil, which is L into B. Tau equal to IAB, where A is the area of the coil.